Good morning to all of you, and good afternoon to those of you on the East Coast. And it is my pleasure to give this webinar. Before I do that, I should acknowledge CESTiCC for funding this project, and also for my master's student, Harry Rodin, who graduated and now is a professional in structural engineering, but the bulk of the work in this research. So I changed the title of my presentation from the webinar series just to make it a little bit more descriptive. So we're going to go over how we recycled retired wind turbine blades and use them as discrete elements for reinforcement in mortar. The use of recycled materials in concrete is something that is a topic that is becoming more and more interesting and more desired. We're looking to be able to reduce the cost of production of concrete as the cost of material goes up, as it becomes more difficult to obtain materials, and also as we're dealing with large amounts of various kinds of waste material now that either have to be disposed in landfills or we need to find a reuse application for them. Also, if we can at the same time reduce some of the carbon emissions of using cement and concrete, and at the same time add to some of the properties of concrete, that's added value products into the mixture. And so with that in mind, our focus here with this feasibility study, with this initial study, was to look and see what can we do with all those retired wind turbines. So the global wind energy industry is on the rise, is growing. And currently, one stat that I was able to find is that we've got 52,000 wind turbines that are in service. Wind turbine blades have a service life of between 15 to 20 years. They weigh a lot, and a good portion of that is GFRP, is glass fiber reinforced polymer. So it's good material. So all of this waste material, piles of it, are going to be available abundantly soon, and we need to have a good reuse application for them. So what we did at WSU is that we worked with those GFRP panels out of the wind turbine blades, and we fed them into a hammer mill and a shredder and kind of resized them into smaller chunks. And then those smaller chunks were further shredded to produce different sizes of discrete reinforcement that we are going to look and see if there is any benefit in using those in concrete as reinforcement. Using GFRP in concrete is not new. It has been used now for decades because of some of the preferred properties of this kind of composite material over steel reinforcement, which has a high strength to weight ratio. It has lower cost of corrosion. We don't have to worry about that. And because of these properties, FRPs have been used in concrete for many different applications. And there is a lot of research, a really good body of research available on how FRPs interact with concrete and how they develop a bond between the two material at the interface, how strong is the bond, and how is the durability of the material in concrete. But our focus is slightly different, whereas we're not using rebars and we're not using laminates or wraps or plates and sheets. We're using discrete element inside concrete. So we are hoping to get a performance similar to structural synthetic fibers, really, with this material. And so some of the properties of and benefits of structural fibers in concrete are pretty well established today. We're looking at fibers being able to mitigate and arrest crack formation in concrete. Fibers are able to bridge cracks and kind of continue that load transfer, stress transfer from one side of the fracture to the other. Some of those increase load at the first crack. They introduce more ductility and strain capacity and deformability to to concrete. They can increase abrasion resistance depending on the type, and also they are associated with some risks. Adding fibers basically adds more weak linkage inside the paste, introduces more porosity typically, which can result in reduced strength, reduced workability. So those are some of the things that we need to work with, and we need to find an optimized mixture design. So for all the different types of fibers that are available on the market, and with all the benefits that they offer, they can vary from glass fibers to carbon fibers to steel fibers, and those all have their different benefits that add to concrete and properties of concrete. What we're looking for is that we're kind of inspired by all of these benefits, all of these properties that current fibers offer, but we're hoping to offer a solution that is not only competitive in cost, but also has a low, small carbon footprint that offers a competitive product that also adds those benefits of the structural fibers to concrete. So that's what we're aiming for. These are the 4 different size groups of the recycled GFRP that we were able to obtain after screening from those wind turbine blades. So we kind of, for abbreviation, call them the large size, the medium size, the small, and powder. And in this graph, I have the frequency distribution of the aspect ratio, length over diameter ratio of the 4 different classes. And as you can see, the small and the powder, those are the ones that kind of hover for aspect ratio in the smaller range. And then the medium and especially the large, those are the ones that have a greater length compared to diameter of the fiber. And more look, the large and the medium, they more look like traditional fibers and what we call fibers really, and comes to mind. And then also one thing to emphasize is that this source of wind turbines that we were able to work with, we ran a thermographic analysis on it, and we know that about 57% of it was fiberglass, and the remaining 43% was a polyester resin. So each one of these strands, as what I want to highlight, is that is not really a glass fiber, it's still that composite material, as those glass fibers embedded within the resin that we're working with. So really the composition is still a full composite material. So we worked in this study with Mortar, and we were just looking to simplify the mixture design and not to have to deal with coarse aggregate variation and size in our mixture. So we just put some Mortar, and we added our glass fiber reinforced polymer to Mortar. We kind of worked over 2 phases in this study. In phase 1, we looked at the effective aspect ratio, and we're looking at those large, medium, small, and powder size groups. We incorporated those at 1 volume fraction, 3%, as a replacement of sand to the original mix, which we're going to refer to as the control, and then looked at some of the mechanical properties. And then in phase 2, we picked one of those aspect ratios, which ended up being the large aspect ratio, and we incorporated that at 3 different volumetric contents of 1, 3, and 5% in the mixture, again at the replacement content of sand, to kind of identify what is the right dosage volume fraction to add this material to the mixture. The only thing that we changed from phase 1 to phase 2 was the water to cement ratio. We decided to increase that to add a little bit more workability to our mixture. So we're going to go over phase 1 results and look at the effect of size or aspect ratio on the properties of Mortar. So since I mentioned this is a feasibility study, everything's small. We worked with a standard benchtop mixing machine, and we mixed our small batches, and we cast the specimens. And the specimen sizes are all small too. So we worked with cubes for compressive strength, small prisms for flexural strength testing, and larger prisms to run alkali-silicate reaction testing. All of the specimens were demolded just traditionally after 24 hours and cured continuously until day of testing in our mist room. So this is basically a list of all the different tests that we conducted on our specimens in the two phases. So first, we're going to measure the hardened unit weight, just to kind of get an idea for if this material, the reinforced material, is decreasing in weight as we expect. And we do that both in phases 1 and 2. Then we will run compressive strength on the cubes. There's a tiny little cube here in the machine. We run test 3 cubes in each test. In phase 1, we're only going to focus on 7-day results to make that period a little short and move on to phase 2, where we focused on a long-term property all the way to 90-day testing. We also conducted bending tests on those beams. Again, in phase 1, we only conducted the test on 7-day, but in phase 2, we conducted the test on all 3 edges. We also recorded the load deflection curve during each one of these testing, and we will use those curves to establish the toughness index of each one of the mixtures. With glass fibers, always there is this concern of durability and the chance of developing undesired ASR problems, expansion problems. So we wanted to make sure that the mix that we are testing is durable in terms of ASR. And so we conducted an accelerated ASR testing according to the ASTM, which includes both heating and also increased alkaline solution. And we took length changes at designated test dates for 35 days. And we only conducted this on the phase 2 specimens. So now let's just start with some of the test results of the phase 1, which will focus on the different size groups of the GFRP. So the first test result looks at hardened unit weight. So after demolding the specimens, we took caliber measurements of their size, and we took weight measurements of them, and that's how we established their unit weight. And just to remind you, the GFRP is inherently lighter in weight compared to the sand that is replacing. So as we're adding more of, or not more of, but as we're adding this material in replace of sand, that unit weight is decreasing and is dropping. And we get a more decrease for the smaller GFRP as they're being incorporated in the mortar. So we are getting that light weight effect by adding this material to the mix. In parentheses, I have the values of p-values after we ran a t-test to compare each one of these unit weights with the control. So those that are less than 5% are significantly different, significantly lighter than the control, which includes all 3 of those materials. So now let's look at compressive strength testing. These tests were conducted on 7-day age. So the control, this is a really strong mix that we've got, and we can see that the results that we obtained for the large size group is very comparable to the control. We start to see a decline in compressive strength for the medium, small, and powder GFRP. And then also in parentheses, again, I have those p-values. So anytime that you see those numbers go smaller than 0.05, that means that those results were significantly lower than the control. So these are some pictures of those So it seems like I was muted for a second. So these are specimens after they've been crushed, just for a comparison. So one of the things that is noticeable is that with the control, you can see that a big piece of the specimen just broken off. However, the ones with GFRP were able to show a little bit more integrity and hold together. For some of the specimens, you can see little pieces that broke off, but nothing major like the control. So looking at the results of flexural strength on 7-H, the control is over here. We've got the strength over here. And then for the GFRP, we're able to see strength increase, strength gain by about 24% for the large. And that is significantly larger than the strength of the control. So this is really good and promising results that we were able to obtain for flexural strength. The other ones are starting to show decline, except for the small compared to the control. So we're going to bear in mind that the large size group provided the highest amount of increase in flexural strength. Now, looking at some photos after the specimens were tested in flexure, we can see that those with the large and the medium, as expected, you can see those fibers protruding from the fracture face. So we can see that they were working for us. They were holding that fracture face together and working the way we were hoping to obtain the benefits from those strands. And now looking at the load versus deflection curves, we kind of established the different toughness indices according to the ASTM standards. So you basically go through all the different deflections and compare them to the peak deflection. So you've got the peak deflection, and then you work with the 2 times, 3 times, 4 times, and 5 times the peak deflection and calculate the area under the curve, area A, B, C, D, and E, and report those toughness indices. And higher toughness indices indicate a larger area under the curve, indicate more deformability, a tougher mix, and that's what we're hoping to gain with the addition of these GFRP strands. So now looking at the test results, these bundle of 3 that you can see show kind of a brittle failure, especially the powder and the control. But what is evident is that large, I kind of increased that area under the curve noticeably. And also looking at the calculated toughness indices, you can see that the large size group is the only one that actually was able to continue to carry that residual load all the way to the 4th and the 5th times the peak deflection. And so those are all really good signs that this mix, the one with the largest strands, is able to continue to carry on, to carry some load and continue to show more deformability rather than this abrupt brittle failure. Based on all of these observations in phase 1, we identified the large size group as the most effective aspect ratio. And the reason for that was that the compressive strength did not drop significantly, and it was kind of similar to the control, and that's what we're looking for. We were able to obtain a significant increase in flexural strength. That's great. Toughness increased, deformability increased, and we were getting more deflections under the load after failure, which was really nice. So with all of these reasons in mind, we picked the large aspect ratio to move forward in phase 2. So this is a close snapshot of that large and the way it looks like. So in phase 2, just to refresh your memory, we're going to now only focus on volume fraction. So we're going to play around with percentages of inclusion of this material in replace of sand. We'll look at 3 different dosages, 1, 3, 5%. We're going to again measure hardened density, compressive strength, flexural strength, toughness index, as well as ASR expansion to make sure that this is a good and strong and durable mix, but also try and identify which one of these contents is the most effective. So we'll start with hardened unit weight. Again, we measured the weight and the volume of both the cubes and the prisms and established the unit weight. And you can see that we can still see that with higher percentages of inclusion of the material, obviously the weight is dropping. So that's nice. We're getting a lighter material, and hopefully we can find a stronger material. these are the results of compressive strength and at all three ages. So we kind of established the whole strength growth curve to compare the three different dosages to the control that does not include any GFRP. So the control will be always shown in black, so it's all the way up top there. And we've got a very comparable results with L1, 1% inclusion, but 3% and 5%, especially 5% shows a decline in the strength. And if you look at those p-values, L3 is still not significantly lower, so it's still kind of acceptable in compressive strength. However, L5 is significantly reduced in strength compared to L3 and L1. So that's something to remember. We don't want compressive strength. We know it's going to potentially decrease, maybe slightly, but we don't want it to decline so drastically. So we'll bear that in mind. We were interested kind of to see how those GFRPs are embedded within the mix. So we threw some of the samples that we cut out of these specimens under the STM and looked at some STM imaging and just kind of zooming in and trying to look at those interfaces. And every now and then you can kind of identify these interfacial zones where maybe there is no bond. As much information as you can obtain from STM, and you can see that there are some areas that you can see porosities, high porosity areas, that maybe those are the reasons that start to result in some declines in the strength. So those are just for information. They're good to see. But overall, it seems like that the GFRP is mixing pretty well and kind of embedded really nicely in the mixture. So let's look at the example photos after the cubes were crushed. And I believe these photos are from 90-day testing. And so one thing that is very interesting is that the control specimen had to be put together, crumbled into pieces without any integrity. And again, look at those reinforced specimens where they're still holding on together. So that's really nice to see in comparison. So now let's look at the results of flexural strength. So this testing, again, conducted over various ages, all the way to 90-day testing. We've got the control all the way at the bottom this time, and now we can see that increasing strength, especially for L5. So looking at p-values, looks like L5 significantly increased flexural strength of the control, and this is really nice to see. This is what we're looking for. We're looking to see increase in flexural strength. But also L1 and L3, even though not significantly, but they were able to increase flexural strength. Here are some photos. The control and the 1% kind of look similar. You still can see some of those fibers. But for 5%, as you can see, the most drastic results, and you can see that the fibers put up a good fight, and you can see the fracture face, and you can see those fibers sticking out of the fracture face. So with those pictures, let's look at the load deflection curves, and let's see what those fibers did with us, for us during bending tests. So the graphs, the load deflection graphs, are provided for 7-day, 28-day, and 90-day testing. And what is really common, the trend that is common in all three graphs, is that the 1% and the control kind of showed a brittle behavior in all test days. And then as we're increasing the volumetric fraction of GFRP in our mix, then we're getting a larger area under the graph, and we're starting to see a more deformable mix that is showing that residual strength now. And that is showing the effect of those fibers sticking out of the fracture face. So if we go ahead and calculate those toughness indices, again, we can see that L5 is the only one that actually went all the way to those larger toughness indices. And also that toughness index is increasing as we're increasing the content of GFRP. So we're basically able to add to the toughness and the formability of the mixture by adding this recycled material to the mixture. And then the one last test that we wanted to run in terms of durability, we wanted to make sure that that content of glass, fiberglass inside the GFRP is not mixing within the alkaline solution, the pore solution, and result in the development of ASR gel, which expands the mixture and results in undesired cracking. So we followed the ASTM standard and ran an accelerated ASR testing. The threshold allowable amount of expansion is 0.1%, and these are the length change measurements expansions that we obtained from the mixture. So you can see that we are well below that threshold limit in expansion for all of the mixtures. And the way I will justify this behavior, I think that it's because we've got that resin that is nicely coating the glass fiber for us. It's a composite material, it's not really glass. So that glass is not directly in touch with the solution to result in ASR. So in conclusions, the size group that we picked is what we refer to as large, and it kind of had a value of around 7 and larger for aspect ratio. And this is still smaller than what you normally see for synthetic structural fibers. And we'd like to test with larger and different aspect ratios in future phases. Then we use that larger size group in kind of the phase 2 of the study, and we focused on different mechanical properties. We saw a slight difference when we included this group at 1 and 3%, but compressive strength significantly dropped when we increased the dosage to 5%. Flexural strength, however, significantly increased for the 5%. So we've got the 5% that can decline compressive strength, yet can increase flexural strength the most. However, we got the 3% that shows both a good compressive strength and a flexural strength. So kind of 3% is ending up being our optimum mixture. All of the three provided better toughness, especially the 3% and the 5%, and all three mixtures passed for ASR. There was no ASR expansion. So we're going to go with the 3% volume fracture based on the limited testing that we did in this feasibility study. We'd like to be able to work with more aspect ratios and more volumetric fractions in the future. We also like to expand the results of this feasibility study to actually look at concrete and look at larger scale specimens. And also would like to look at different compositions of GFRP, different types of resin used in this material. So with that, I'd like to wrap it up, but I have to acknowledge my PIs, Dr. Hui Li and Dr. Carl England, who take care of the recycling, resizing of the wind turbine blades, and provide the fibers to us to be able to use in concrete, all the graduate and undergraduate students that help with the extensive work in the lab, and of course CESTiCC for providing funding, and Global Fiberglass Solution for providing the original material and for additional matching funds. Also Premix and Ash Grove Cement continuously support our lab with cement and aggregates, so we say thanks to those as well. These are the list of references that I used throughout the presentation, and thank you very much for your attention. And please go ahead and type your questions. I'd be happy to answer any questions that you may have.
Yeah, I'm going ahead and unmuting all attendees so that questions can be asked. So you can mute yourselves if you're not interested in asking any questions, but oh. All right, now it's complaint. All right, there we go. Doesn't want to let me unmute some people. So if you have a question, can you post it? Okay, you got people who are self-muted. So that's fine. Any questions? All right, if there are no questions, then I will let everyone know if you need a professional development certificate, please send me an email. I'd like to thank Dr. Nassiri for presenting, and I will end the webinar. So last call for questions. Okay, thank you very much. And there, you will all be receiving an invitation to soon to next month's webinar. Thank you very much.